Welcome back to the last and final session for the Basic Mathematical Intuition for Robotics course. Thank you all who have actually stayed from session 1 till session 5 through all of our classes, and hopefully all of you have learned quite a bit to what goes into actually modeling a robot. This is going to be our last session for this course, after which we are going to have another course which is going to be practical mathematics for robotic applications, which will start on the coming Monday. That course will go more into detail, much more detail for all of the math that's actually involved, and will actually practically do it. So quite a few people have already joined this live stream compared to the past few days, so we're going to get right into it without any further ado. So just to have a quick recap of what we did in the last class is that we realized that we could use the Jacobian matrix, which could be found by quite a few different methods, geometrically using that table and other such methods. We could relate the following things. We could relate the differential motion of the joints to the differential motion of the end effector, which meant just by seeing the tiny movements of the joints, we could see how those tiny movements are actually going to affect the movement of the end effector. The second thing that we could relate were the velocities of the joints. So we could see how the different speeds of the joints would cause a different speed in the end effector. So once we know what the speed of the end effector should be, we could figure out what the speed of the joints should be to get the same speed of the end effector, to get the required speed at the end effector. The third thing was we could calculate what the force and torque would be on each and every single joint given the force and torque that's acting upon the end effector. All of these we could do using the Jacobian matrix. But the real question is, how do we actually control the velocity of the joints? We know that, yeah, we could figure out what the joint velocities should be. We know we want the end effector velocity to be like, let's say, 5 meters per second. So using the Jacobian, we could find out what each of the joint velocities should be. And using trajectory planning, we could also see what the motion of these different joints should be. But how do we actually control that motion? And that's where we come into this session, which starts off with systems and controllers. So first we're going to be talking about what exactly a system is. And a system is anything which can be modeled mathematically. So systems are of many different types, and we could have thermodynamic systems, we could have thermal systems, we could have electromechanical systems, and so on and so forth. But for robotics, there are three main systems. And the first type is a mechanical system. The second is electrical, and the third is electromechanical. So a mechanical system would be of this form, where we have different masses and we have different forces acting upon those masses. Whether it's just a push, whether it's a spring force, whether it's a dampening force, all those different forces acting upon these masses. And we all know from, I guess, 12th standard physics, first year of engineering, civil, all of those, we could figure out what all of the equations of these motions would be. And yeah, if there's a force acting, we know force is equal to m into a, and a is actually the double derivative of x. So we could actually model this as a differential equation. The next type of system, electrical system, would be of this form, where we have inductors, capacitors, resistors, voltage sources, currents, and things like that in literally any configuration that we could think of. Even this could be modeled mathematically, because we all know that current, we could calculate the current through an inductor. We all know voltage is L di by dt, and voltage across a capacitor, we know the current across a capacitor, the voltage across a capacitor, 1 by c integral of I dt. And all of those things we could actually calculate and model them mathematically. And remember, since again we had an integral term, we had a differential term, this would also be a differential equation when we actually model it. The last type of system that robotics is generally worried about is electromechanical system, which could be something like a motor. In fact, the example I've taken here is a motor. There are so many others, your galvanometers, ammeters, voltmeters, they are all electromechanical systems. But essentially, there has to be some mechanical portion which is driven by electricity. It could always be the other way around, like a generator where we have mechanical forces driving the electric circuit. But either way, there has to be an electrical component and a mechanical component, and that's what an electromechanical system is. And this is how a motor would be modeled. So the real thing is that when we're modeling all of these, we said that they are differential equations, and differential equations are very hard to solve. So to avoid that problem, we've used something called the Laplace transform. So the Laplace transform, I'm pretty sure all of you who are in engineering, who have finished the first and second year, or you're currently in second year, you already know what this Laplace transform is. You've had it in math courses, and it's a relation between what I guess is taught to you in math as the time domain and the frequency domain. So what it really is that because differential equations are hard to solve, we use these Laplace transforms to convert these differential equations into algebraic equations. And that's because if you take a differentiation in the time domain, which is d by dt, in the Laplace, once you do the Laplace transform, which is the Laplace domain, which is the S domain or the complex frequency domain, it becomes S into whatever function you were differentiating. So if you had di by dt, if you take the Laplace transform, it would just be S into I in terms of Laplace. So we would call it I in the frequency domain. If you had a double derivative like d squared by dt squared, it would just become s squared, which is again algebraic. There's no more calculus involved. If we had an integral, for example the integral of I dt, that would become 1 by s. So integrals become 1 by s and derivatives become s into whatever, and that actually makes it from a differential equation into an algebraic equation. So Laplace transforms convert everything from the time domain into the S domain or the complex frequency domain. So depending on this, we will get something called a steady state error depending on what the type of system is. And we won't get into type of the system and all in this particular session or in this course. We will talk about more of what type of a system is in the last session of the next course, which is practical mathematics. So just to show how systems are modeled, we've actually modeled a small system over here, and just to show that you can't even tell that what system this is, whether this is a motor, whether this is a galvanometer, you don't really know. The only thing that you know is that it is simple to model. You have a few S terms, you have a few terms with S, and you have them all going from one place to the other and eventually giving us an output. You feed in an input and you get an output. So for example, this particular system has a steady state error equal to 5. We have a final value supposed to be 5, but because this system has a steady state error of 5, you can see that our output actually goes all the way down to 0. And remember that there is something called an overshoot, so it's never really 5. There's always a lot of fluctuations. And we'll get into that in a few seconds. But the basic system, this is just so that you know that, okay, this is called the forward path, which is going straight in, and there's something called feedback, and the feedback, which is the output multiplied by some value. In this case, it's actually being integrated and multiplied by 8. and it's being given back and it's being subtracted from the next input, and that subtraction says that this is a negative feedback. We could also have positive feedback and so many other things, but we'll not get too much into that. Hopefully this just gives you a general idea that most systems will have a forward path and some form of feedback. Some systems do not have feedback, and those are called open loop systems. But when you're creating a robot, most systems will be closed loop, so you will have some form of feedback. So we've actually modeled here a DC motor, and if you actually look at the DC motor consists of two systems. It's an electromechanical system, so it has an electrical subsystem and a mechanical subsystem, and there is some feedback relating the two. But the electrical subsystem itself consists of all of your inductances, resistances, and there's an integrator and things like that. We won't get into why exactly this is this, what we're adding and all of that, but you just have to know that there is an input being given, which is voltage, and there's an electrical subsystem, there's a mechanical subsystem, which consists of your torque constant. It consists of all of your different mechanical variables, and eventually you get an output, which is the speed of the motor. So the speed of the motor, if we were to run this right now, let's not look at the PI controller just yet. We'll get into this in a second. But right now, the DC motor, the input to the DC motor is this 9 volts that's going right into the DC motor, and we're getting an output. If you think that this is disturbing, we'll remove that as well. So right now it's just 9 volts entering the DC motor and giving us an output. So if we actually run this simulation, we see that the output of this motor, once the simulation is done, is going to be like this. The y-axis over here is the speed of the motor, and you can see that it is very, very unstable. This eventually reaches something called the steady state, and we can see that the speed at which it finally settles down, if we zoom into this bit, is around 224 rotations per minute. So we have 224 revolutions per minute, and before we actually reach that steady state, the motor really oscillates. The speed goes up, then it goes down, it goes up and down, and that's really how a practical system behaves. So right now we put in a voltage. We put in a voltage of 9 volts, and we got our output at 200 and something rotations per minute. But what if that's not the speed that we wanted? How do we actually control what this speed is? So for that, we go into controllers, and we're gonna get into the controllers. So the first kind of controller, in fact the main kind of controller, is called the PID controller, which is proportional, integral, and differential controller. So controllers don't necessarily have to have all the proportional, integral, and differential components. It could be a proportional controller which would just have P, just integral, just differential, or PI, PD, etc., etc. But in most cases, you'll find either a proportional controller, a PI controller, or a PD controller. You don't generally have just integral, just differential, or integral differential controllers as such. For most robotic applications that I'm talking about, you would use PID or PI controllers. So what exactly is this PID controller? A controller would take in the error signal as the input and provide a correction factor as the output. So the error signal is actually the difference between the current output and your desired output. So if we wanted rotations per minute as 157, the error signal would actually be whatever the current output is, which we got was 200 and something, minus 157, which is our desired response. And that error is what would be fed into the PID controller. And the output would be given as a correction factor, which has to be added to the actual input. And we'd finally reach our desired output eventually. So this is actually what the PID controller does. This is the math behind it. it has a proportional constant, which we call Kp, which is just a constant multiplied by the error. That's why it's proportional. It's just straight up multiplication. So if we had just a PI controller, this is what the correction factor would be. If we had a PI controller, there would be this. Along with that, we would add in the integral of the error. So why would we add in the integral of the error? We'll get into that in the next slide. And a PID controller, we'd also add in the derivative of the error. So what that looks like is this particular graph right here. It looks pretty complicated, but let's get through what it is. In this case, the example that I've taken, it's actually a temperature that they're looking at. So the desired temperature is this red line over here. We want a temperature of 40 degrees Celsius. That's what our desired temperature is. But let's say that we did not have any controller. Let's say we have a microwave that's heating things up, and we want to heat it to 40 degrees Celsius, which is just a bit higher than our atmospheric temperature. If we did not have a controller added into it, without any regulation, and we just kept it on, it would eventually reach 100 degrees Celsius. It would just keep, suppose it was water, it would keep heating it till eventually the water reaches 100 degrees Celsius and starts boiling. And that's what this graph is, no controller whatsoever. But if we do have a controller, we have some sort of error signal being calculated, and then we're trying to control it. The first type of controller we could do is the proportional controller, which would, as seen right here, it would just be Kp, some constant, into that error. So right at the beginning, we start off, there's an error of 40 degrees because we started off at 0 degrees Celsius. So we'd see, okay, there is some error, so the microwave would be on, and we'd add that in. We'd increase the temperature of the microwave. We'd increase the temperature of the microwave so that it heats up fast. And once it starts heating, we see, okay, there's still an error, so we're still going to keep heating. And then we continue to heating till we see, okay, now the temperature has crossed our desired response, and now we have a negative error because right now our current temperature is greater than the desired response. So it eventually starts cooling the entire system down. And we start cooling the system down, and we reduce the temperature. When we say cooling, we're not going to have it at 100 degrees. We're going to reduce it to maybe, let's say, 20 degrees Celsius. So now the system starts cooling down, and then we see, okay, now the error is lesser, so we add it back up. And we keep heating it, cooling it, heating it, cooling it, till it eventually keeps oscillating till it reaches what's called the steady state. But note that here there is a steady state error. We will have some error if we're using just a proportional term, because eventually you would keep switching it on and off, on and off, on and off at an area which is not equal to 40 degrees Celsius if you're using just a proportional term. So the next thing that you could do is add in an integral of the error. Now what happens is when you're adding the integral of the error, the moment it actually starts crossing, because of that integral, we have a greater overshoot because we're adding in all of those errors. We have a huge overshoot and an undershoot and all of that. But because we're adding in the error every time, even if we were to reach a steady state here, we still have an error, and that error would be added, and that steady state would reduce. That steady state error would reduce, and that error would reduce till it becomes zero, no matter what we did. If you try getting out of this, there would be an error which would be added, and it would come back down to the final steady state. So we'd actually get zero error whatsoever, zero final state error. Steady state error is what we call it. So there would be zero steady state error if we were using a PI. But the problem is, as you can see, here we reached the steady state right here, which was like pretty soon. But when we're using a PI controller, we're reaching the steady state much later, and there's a huge overshoot. It's oscillating a lot. So to reduce that, we use in the derivative term. Now remember that derivative is actually the slope. So if we're changing really fast, the value of this derivative is going to be really high. And if we're not really moving, the value of the derivative is going to become 0. That's why once we reach steady state, the slope, which is the derivative, the slope is going to be 0. So we're not going to be adding or subtracting anything, and we can actually ignore this, and it just becomes like a PI term, PI controller, which gives the output the steady state error as 0. And because we have this derivative term, these slopes are cancelled out. We take care. If the slope is trying to move too fast, we have a higher derivative term which flattens out that slope. And we eventually get this nice curve which does not have too many overshoots, reaches the steady state much faster, and has a steady state error of 0. So we're going to actually look at that with our example, with our motor that we have right here. Oh, by the way, this is MATLAB. We're showing the simulations on MATLAB. So this 9 volts, we're going to add in the 9 volts directly to this summation, which is the output of the PI. This should actually be a PID controller. So we're going to keep changing them. PI, we're going to do a P, PI, and PID. So right now we have this setup, and we're going to have the output of the correction factor added to the 9 volts to give what the value of the motor should be. So the PID has to have an input of the error signal. It will have the difference between the desired response, which is 157 for the example that we've taken, it's 157, and the actual response. It has to have the difference. So we have to feed in the actual current value. So we're going to feed in the actual current value right there. So we're going to be taking the value and putting that in, and the desired value of 157 RPM in as the first input. So here we have the two inputs that are getting subtracted, so we get the error signal. So now we're going to first have just a P controller. So the error signal is going to come up, get multiplied by Kp, the constant, and that's what's going to be added as the output of the P controller. We're not going to add in the integral and the differential components yet. So we're just going to see what the output is when it's just a P controller. So we all remember what the output of the DC motor was, and it was at 220 something. So now when we run this simulation, and we're running it just for 10 seconds, we can see that the output is going to be a lot of oscillations, yes, but the output's not above 200 anymore. The steady state output is 162. It's actually 162. We did aim for 157, but there is some steady state error, which proves what we said in the previous slides. There is some steady state error because we wanted 157 as our final output. And if you actually zoom in close enough, you see that there is some other changes that are happening. Okay, so let's get out of that. So that was just the P controller. If we added in the integral component, we have some value of Ki. Now this Kp, Ki, and Kd, these values, you just tune them. You keep changing them till you find something that you like. For most cases, of course, you can formally figure out what they should be, but in this case, we've just arbitrarily taken things that gave us output similar to what we wanted. So now if we actually run the simulation for 10 seconds, you won't be able to see the output. We saw there, if we were to go back here, we can see that we're reaching the steady state by around like 5 seconds. Within 5 seconds, all of our oscillations actually stop, and you can see that there are oscillations that are happening. My mouse is, something's wrong with my mouse, but okay. There are some oscillations happening, and that stops by around 4.5 seconds. So by 4.5 seconds, we actually finish reaching the steady state. So now what happens is we have that, and we're going to add in this integral term. So now we're going to run the simulation with this integral term, and we're going to actually bump it up to 15 seconds because I know that 10 seconds we won't be able to see it reach a final steady state. So within 15 seconds, if we actually look at the output of this controller, we see that it takes about 10 seconds to, okay, it takes 10 seconds to reach, but no, that did not work. We've connected in the integral component, yes. Output, okay, this should have worked. Let's just wait for it to run the simulation again. No. There is something wrong. Wait. I think I'm gonna close this once and just reopen it. On MATLAB itself. Just bear with me for a second. Oh, well, I can't. Okay, there we go. Okay, so as this opens up, there. Now let's see if this is okay. Yeah. So let's just run the simulation again. It should work. It definitely worked while testing it out. There's no reason why it should not be working. So yeah, now that we look at it, there's still some error. Why is there this error? I have no idea. Oh god, I just closed it again. I don't know why that error is coming, but okay. There's some error and we'll figure that out soon. But before that, let's just try adding in the differentiation term and let's see what happens. So let's just run that and let's see. Maybe there is some connection error. No, everything in the DC motor section also seems fine. It should have worked. Yeah. Okay, so right now we have 160 coming out. We still have that 163 itself that's coming out. We don't have the desired value, but you can see that the entire oscillations have been cut out on adding the D term. Why is that? Maybe because we should be having this as a product. Let's just try that out. This is a correction factor. I have this on add. It should be a product, and let's see what happens now. If we just have PI and we run this simulation, we go back, we wait for the simulation to finish running. Whoa. Yeah, so it eventually reaches, it is a correction factor, so it does reach the steady state and it does take a lot of time for 14.6, and it is reaching the steady state of exactly 157. There are small oscillations, but even those, if we were to have the simulation for long enough, even those oscillations would eventually die out and become nothing. So we can see that just by adding in the integral part of the controller, we could reach 157, which was what we desired. We did reach exactly 157. But because it's a PI, there's a lot of oscillations happening. And of course, since we showed you the P with just an addition and we didn't have the thing, if it was just proportional, we would still have that steady state error. Don't think that the same problem is what caused it to reach 160. We get that steady state error even if we do have just the P controller, and that we can see right here. Okay, let's just zoom in. We have a steady state error. Yeah, there's a negative steady state error. You can see that it is oscillating about 155-ish, and it's not really oscillating to 157, which is what we wanted. So we wanted it to reach 157, but it isn't. There's a steady state error right here. And you can see that, yeah, it does oscillate within that much itself. It doesn't ever reach 157. It remains at 155, slightly above that. It doesn't reach 157. So that was the steady state error. So if we did add the PID, we showed you P, we showed you PI. If we add in the PID and we have the derivative part of the controller, it's a correction factor, so it should be multiplied. So once we have that and we actually look at the output, we can see that we can get it to exactly what speed we want, and we wanted it at 157. It reaches 157 itself, and it reaches that much faster. You have to go into where it actually settles down, and we see that it is exactly 157, and it remains at 157 constantly with a PID, and there are very little oscillations. You can see there's a little bit of oscillations happening over here, but those oscillations do die out. And that's the cool thing about a PID controller. There are oscillations, but they all die out, and you eventually reach the exact steady state that you were looking for. So that's what a PID controller is. But we just saw that we needed to know the actual output. So how do we find out the actual output? And that comes to the last part of this session and the last part of this course, which is encoders. We generally use encoders with a microcontroller that uses timers and interrupts to figure out what the speed of these motors currently are. That's how we get the actual speed. And if you want angles, we use something called absolute encoders. So an encoder can be of two types, linear and rotary. So rotatory. Linear encoders are for prismatic joints. Rotary are for revolute joints. Linear encoders or rotary encoders, in fact, rotary encoders can have all of these. Each and every single one of these can have all of the same subcategories. They can be magnetic, laser, optical, and there are actually many more, but the most used are magnetic, which uses a Hall effect sensor, lasers, and optical encoders. In fact, for our examples, we'll be showing you optical encoders. So they can either be absolute or incremental. So incremental cannot tell us the position of that motor. It can tell us only the speed. And in fact, by having a disk like this, you can actually say which direction it's moving on. Because we'll get into that a bit in a few seconds. We'll actually show you. But the thing is that using an incremental encoder, you can only tell the speed and maybe the direction. You don't necessarily have to be able to tell the direction, but you can only tell the speed, maybe the direction. Using an absolute encoder, you can tell both the direction and the current position, the angular position of the motor, and the encoder would look something like this. Both of these are rotatory encoders. So if we just look at an encoder that I model them out over here. So this is what an encoder would look like. This is a linear encoder, and this is how an optical encoder would look like. This optical encoder would be able to tell us only the speed of the motor. So if we had some wheel and axle connected, if we have a motor on top over here, we'd have this connected to the shaft so that this rotates, and whatever is being rotated would be down here. So when this rotates, it would pass through a device that would have probably a laser here or an optical something that gives out light over here, and we'd have a sensor right here, and this sensor would calculate the number of times an opaque disc cut that laser. So when this rotates, it would cut the laser, and we would be able to see what speed it's rotating just by seeing how many times it's being cut per second. How we would do that is we would connect this up to a microcontroller and have something called an interrupt, and I'm sure most EC and EEE students have studied this. So we'd have something called an interrupt, and using the interrupt service routine, we'd be able to actually mix with the counter. We'd be able to count the number of steps it took before the next interrupt was called, and by knowing the clock frequency, we'd have to calculate exactly how many seconds it took. And once we know how many seconds, we could calculate what the speed of the motor was. If this was connected to a wheel or something, we could know how much distance the robot moved by using these encoders and figuring out how much the wheel has actually turned. We can't do that just by measuring the voltage, because even two identical DC motors would have slightly different speeds for a given voltage, because they're very, very sensitive devices. So we really need to know what it practically is, and we really need a controller to take care of it. Now, an incremental, the one that we saw over here, okay, and in case it's a linear, this particular thing would be placed right here. This one would be moved out, would move really fast like this, and we would be able to tell in what speed the joint is moving. So incremental, if we had something like this was the serrated disc, we would actually have two sensors over here instead of one sensor and instead of one laser and one sensor, one laser here and one sensor here, we would actually have two lasers and two sensors, one for each of the holes. So depending on which sensor is receiving the laser first, we'd know if it's rotating clockwise or anti-clockwise. If it is rotating clockwise, always the sensor that's over here, the one that's reading the outer peripheral laser, that sensor, it's receiving it first. That means the disk is rotating, the motor is rotating clockwise. If this one is reading it first, it would mean that it's rotating counterclockwise. Whereas an absolute encoder has binary encodings that would actually tell us at what angle it is. So if only this one is receiving a signal, that means it's at some angle. And if these two are receiving it, it's a different one. If it's just this one receiving it, and you know this is actually going in binary: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So that's how this is actually going. So this is going up to 16. So it's going from 0 to 15. So we could actually get 360 divided by 15, and that would be our angle's error, but we would know within that much how much it is. And we could actually figure out exactly what angle it is, what direction it's rotating, and what speed it's rotating with. And the cool thing is, these stuff go really, really tiny and really, really accurate. So you can imagine that this would precisely tell us lesser than an angle of the motor, and this could tell us very precisely how fast it's moving. And with that, we come to an end of this session. We come to the end of the 5th session. Thank you all for joining. If you guys have questions about this session, you can start asking all of the questions now itself. Right from now, we will answer all of the questions of this session from now. But till then, we'll just have a quick recap of all of the previous sessions that we had, and we'll just go through the journey of how we got to this session soon. It should take us another 10 to 15 minutes at most. So we started off our first session talking about the categorizations of robots and how they're generally categorized conventionally. But we saw that for robots, we couldn't categorize them conventionally, and we had to have a new method of categorization, which would be based on the joints, which could be revolute or prismatic. The revolute or prismatic joints we saw looked like this. We had a revolute joint which could move about only one axis. We had a prismatic joint which would move along one axis. It could only move along one axis. We saw that if we had one joint, they're gonna move only about one single line, either a circle or a line. So we came with planar robots, which could be 2R or 2P and stuff like that, and they could reach any point in a two-dimensional plane. And so yeah, they could move any place on a two-dimensional plane. And that's what we saw for planar robots, and they could be of a third type which could have one revolute and one prismatic joint. But to reach the third dimension, you needed another joint which could make three more categories of robots. So the Cartesian could move anywhere along the they could move anywhere along the x, the y, or the z, and we could get any possible place in three-dimensional space. Another type would be the spherical robot, which could rotate, which would give us a value of theta. We'd get a value of theta, we'd get a value of phi, and finally a value of r, which would give us anything in a three-dimensional space with a workspace of a sphere. Cylindrical robots, same thing, r, phi, r, a height, and of course a radius. So that's what a cylindrical robot was. We saw that we could have multiple more joints, and that's why we had to name them in a generalized fashion, which would be 2r, 2p, 1r, 1p, and so on and so forth for any number of joints, whether they're prismatic or revolute. Next, we came up with the concept of frames, and we saw that points are represented in terms of matrices, and they would be column matrices, and everything is mentioned as with respect to frames. So we would always have a point with respect to frames, and as you can see, frames really do change. So we had to find out, if we knew the point with respect to one frame, how we could find the point with respect to another frame. And that other frame could really be rotated or moved about by any single way, and we'd still have to find out what is this point with respect to this frame, as long as we know a relation between this frame and the original base frame. We'd have to know what angle it's rotated by and what angle it's moved by. And that is what we actually ended our first session with. We saw how to take care of translation, which is just movement, and how to take care of rotation. And our next, we also said that the rotation could be about the moving frame or the fixed frame. That means we could be doing the next rotation about the original base frame or the new rotated frame. But apart from that, that's what actually caused us to come to our next session, where we found an overall transformation matrix. So the overall transformation matrix had to do something like this, where we first rotated the frame and then we translated it to find out what is that point with respect to the new frame. And we shrunk this huge equation into one single transformation matrix with just multiplication, because it had multiple values, such as finding the inverse, and also the fact that you could multiply to get from one frame to the other to the next, and so on and so forth. And this transformation matrix consisted of a rotational part, which would show us the rotation to go from the base frame to the last frame, and also the origins. It would show us what the different relation is between the origin of the original frame with respect to the new frame. And with that, we found out the properties of the transformation matrix, the fact that you could just multiply them to get it from one frame to the other, and also the inverse of the matrix. And we saw that, okay, to get the matrices, we need a single process to take care of all of the variables as well. So we came up with we learned about the DH parameters, where we would go from the step one would be to assign frames. So let's just get rid of this. Step one would be to assign frames. So we can see we have the base frame here, first frame. So this is actually the base frame. So 0 to 1, 1 to 2, 2 to frame number 3, and 3 to the final end effector frame, which is 4. And each of these, remember, we have to have one frame assigned for each joint, and each of them will have one particular variable. So with this, seeing these particular frames, we could fill in this particular table, and with this table we can actually find out the transformation matrix from one frame to the other by filling up these values from the table. And then we could multiply with this particular equation and find the final transformation matrix. And we call this as kinematics. So the forward kinematics, using the joint variables, we could find out where the end effector is. Inverse kinematics, knowing where we want the end effector, we would have to find the required joint variables. That was the end of session 2. Session 3, after that, started off with the fact that we could actually design trajectories for these specific joint variables. The trajectories could be of two types, which were point-to-point and continuous. Point-to-point would be pick and place, and continuous would be for things like welding, painting, and stuff like that. Point-to-point, we didn't bother much about the intermediate path followed, so it could be like this. And we didn't necessarily care if it actually touched the middle point. We would just have via points, as we call, and it would go through. And we would need this because inverse kinematics is computationally painful for a robot, for the microcontroller. So we want to have the least number of computations required. Whereas continuous, we would really care about the path that they're taking. And for that, we'd actually have to do the inverse kinematics for every single point in between, as many points as possible. So it would be very, very slow, but it would be necessary for things like welding and stuff like that. With that, we came to the difference between joint space and task space, where we said task space was actually the world coordinates XYZ, and that is what most people would, the most users would be talking about. Whereas the joint space is actually the values of the joint angles and the joint variables like theta and L, which would actually tell us using forward kinematics where the end effector is in the task space. They all had their advantages and disadvantages that we looked at in the class. And then we came about point-to-point trajectory planning. So trajectory planning, it could be linear, where we just went from point A to point B to point C just by changing the value of theta linearly. Now we saw that if theta changes linearly, the final output would not actually be the final end effector's velocity. The end effector's trajectory would not be a straight line necessarily. As we saw in our example, the end effector was actually pretty much going in a curved manner. And we'll see that again today because a bit of this had gotten cut off while we actually went through it. So this could be one way of point to point. And remember that doing this, we don't have any control over the speed at which these theta is changing. We don't have control over the speed or the acceleration of the change in position or the change in velocity. So we came up with something called the cubic spline, where we said we're going to change theta according to this equation, which has four different constants, four different variables that we could actually change according to what we want it to be. So by changing these four variables, we could actually change what the speed of this joint would be. So we could find out the exact speed of the joint and determine it. And that would actually cause theta to vary something like this. And what happens there is that we get finite values that we can actually accomplish with our physical motors. But the cubic spline does not give us control over acceleration, and we still have no control over the acceleration. So we went into a quintic spline, which could actually control the acceleration as well. And apart from this, we could go higher and higher, but we didn't necessarily need to go that high. So we went through something called parabolic blends, where that, okay, maybe cubic splines would also require a cubic equation, which is pretty big. So to change direction, we also knew that the smallest possible equation that we could use was the equation of a parabola. So we'd actually blend it in like this. So we'd follow a straight path, but just as we approach the point, we'd follow a parabolic curve, because parabolas are just a quadratic equation, which is much lesser than a cubic equation. So just by using a quadratic equation, we could get this turn, and then again follow a linear path till we reach the next point. Now the thing is, as you see, we don't actually reach the point, and so that's what we had over here. We could actually see that we don't necessarily need to reach the point. So in this case, to go from this point to this point to this point, if we were moving linearly, you can see what the trajectory of the end effector is. Remember that we are just looking at this particular angle of this particular joint, and this is a 2R robot, and our aim was to add in this via point. We have to go from point A to point B, but we added in this via point just to ignore this specific obstacle. So yeah, just by changing these, we were able to reach all of the points. We were able to reach this point and not hit this. But the problem is, so apparently the last few seconds were cut off, so we'll just go through the last few seconds again. So if you can see, we can actually go from one point to the other. By adding in these via points, we could actually make sure that we're avoiding this obstacle. And if we were to use this parabolic blend, as you can see from the diagram, we're not actually going all the way down to what the theta value at B was, and we just go back up. So if we do not go that low, we end up here. See, theta value, we were supposed to go this low, but we don't. We see that we do not reach the point. We actually do miss the point, but we're still not hitting the obstacle. So it really doesn't matter if we actually reach that point or not, as long as we are missing the obstacle. And that's why parabolic blends work. But in case we do necessarily have to reach this point, we really want to reach the point for some reason or the other, we do something called adding pseudo points, and we have this final point on the linear path between these two pseudo points. So an example would be like this. To reach this pseudo point, obviously the linear section over here would rise, and we'd have a parabolic blend over here, followed by a tiny linear portion which passes through C. Just assume it passes through C. It's been really badly done, but still, it does pass through C. And then there's another pseudo point C dot, which has a parabolic blend, which causes it to eventually go back down to wherever the next point is. And that was parabolic blends, and that was the end of session 3. With that, we came to session 4, where we spoke about how do we actually figure out what the joint variables should be when we know what the final velocity should be. So for that, we actually created Jacobians. We tried to find out what a Jacobian was, which would be a matrix that would relate the joint variables with the final world coordinate velocities, the linear velocities in the x, y, and z direction, and the angular velocities in about the x, y, and z directions. And we did a small example with a cylindrical robot. We found out what the entire Jacobian would be by geometry and differentiation, and we saw that okay, it's possible for a small cylindrical robot, but once it gets more complicated, finding these values itself becomes hard, and differentiating those become even harder. So we went through figuring out that okay, what the dimensions of a generalized Jacobian should be, and once we know the dimensions of the generalized Jacobian, we could actually fill in each value by using this particular table, where we had the rotational matrices that we get from the transformation matrices in the DH parameters, and multiplying all of those as such and filling it in to get the Jacobian values. Apart from that, if we couldn't go through that method, we'd actually use something called propagation of velocity, where we'd start from the absolute base frame, see what the velocity is for each and every single joint, and we'd see, okay, the first joint moves by 5 meters per second, which causes the second joint to also move at 5 meters per second, but the second joint itself is moving by 10 meters per second, which causes the third joint to move at 15 meters per second, and so on and so forth. So we use these formulae to go about finding both the linear velocities and the angular velocities from one point to the other, and the formulas changed whether the next joint was rotational or prismatic. And with that, we also did the last thing, which was force and torque, which told us what force is going to be acting on our prismatic joints, and what type of torque is going to be acting on our revolute joints, given a force that is acting upon our end effector. And there were two methods. One was back propagation, where we know what it is at the end, and we find out what it is for the previous frame, and we keep going back and back till the first frame by using these formulae. But if we already knew the Jacobian, we could use just the Jacobian that relates the final frame to the base frame, the transpose of that, and multiply it with the X, Y, and Z components of the force acting on our end effector. And with that, we had come to the end of session 4. Then we started our final session, today's session, and that was systems and controllers, where we saw that we could model everything as a system, which could be mechanical, electrical, or electromechanical in case of robots. And we found out that they're generally modeled as Laplace transforms, because that makes differential equations into algebraic equations and easier to solve. These particular systems would have a steady state error, and that steady state error is removed using the PID controller, where each of them do a different thing, and we eventually get zero error. And to use a PID controller, we need the real-time values. What is the current speed to calculate the error? And that we would do using encoders, which we would put in using timers and interrupts in a microcontroller. And with that, we came to the end of this session, end of this course. Any questions at all, anything, we are open to address them. This was a 1 hour class. We said in the email that it'll go on for 1 hour and 10 minutes. So we have another 12 minutes, I guess, to address any questions related to any of the sessions, related to this course, related to the next course, related to the club, any form of feedback. If you guys have any feedback, any suggestions, you thought it was boring, interesting, good, bad, do let us know right now so that we can rectify them in the future upcoming sessions, upcoming videos, and literally everything. I still don't see any questions coming up. There is a 20-second lag between from when I ask questions to when I receive questions from you people, because of YouTube's live sessions. Remember that these courses will be removed from the IEEE RAS YouTube page on Sunday in the evening before the next course starts. So tell everyone you know to watch the sessions by this weekend. They still have 2 more days. Please watch through all of them before they go. Remember that this is the basis for the next session. The next session is very, very technical, very, very mathematical. It is engineering level of robotics, and hopefully after that all of you can model robots. Till you guys actually ask me any questions, I'd like to mention that hopefully this course, the aim of this course was to give you guys a mathematical intuition of what actually goes into designing a robot. Each robotics is a very interdisciplinary field. It consists of so many different fields, which is both control systems, mechanical, electrical, electronics, CS, electronics and communication, everything. If you think of any domain, robotics can either be used in it or that domain is used in robotics, which makes robotics one of the most extensively usable fields in current day. So hopefully more and more people would start getting themselves exposed to robotics, and there's no better way to do that than to actually pick up different components and start building something. There are so many projects out on YouTube, out on Instagram, out on the internet, GitHub, Instructables, so many places where you have open source projects where you get all of the components necessary and everything else that's necessary for it. And I think that's a great place to start. Of course, the projects are made so that you don't have to code anything, you don't really have to design anything. Everything's designed, everything's coded. You just have to hit a few buttons, upload, maybe make a few changes, and you're done. You've actually created a robot. And I think that's a great place to start, because that's what gives you the motivation to become the person who actually does the designing, does the coding, and does everything and makes it available for others to get the motivation to start making different robots. I still don't see any questions. I think I can assume that nobody has any questions for this session or any of the previous sessions. I don't see any of the chats appearing here either. So hopefully everyone can relate to the fact that as a child, science is very, very interesting. But as they grow up, students tend to drift away from engineering and science. So maybe we really have to start getting more exposure to that, to all of these different domains in simpler ways so that people do not lose that in certain types of robotics, even in underdeveloped nations as well. But the thing is, if you do want to go into robotics or maybe have a startup, hopefully you guys can hear me. If you can't, I will type this in as well as a comment. But yeah, robotics, if you do want to have a startup or you want to actually go into a field, the field of robotics is very, very important. Robotics can be of any type. It can be of many, many types. You could have household robotics, like cleaning robots that are just going to clean up the room or clean up your floor or help out in dusting and things like that. But the problem is those robots would not be as cheap as labor in India. Human labor in India is not that expensive. We all have maid servants that we are paying lesser than what we would have to pay for a robot. So people would prefer that. So if you do think of going into robotics of that sort of field, you might not get as much of a response as you'd want. Although that type of field would work really well in a country like USA or places where human labor is very, very expensive. On the other hand, robots in technical fields, maybe like medical robotics in India, hospitals would be willing to pay for very precise robotics. And of course, there the robots would be very, very high. And the problem is you would not get that much of funding as a startup. But you could always join a company that's already making medical level robotics. Maybe that's not a great startup idea, but there are companies that are working with huge amount of innovation in that level of robotics, industrial robots, and India is investing in those kinds of robotics. So that is a good place for you to try in for robotics. So there is a huge amount of scope, but it really depends on what kind of robotics you are working on. Whether it's small household robots that can be done using manual labor, or whether it's high-end robot which adds in a lot of value to what you're doing. Whether it's uh, reducing the risk of human error during a surgery, or whether it's increasing the precision to a very, 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 very accurate amount, so a high amount of precision. So hopefully that answers your question. Please do let me know if that answered your question and you could hear it. If you could hear it, if you reply in another 20-30 seconds, then I won't type it out. Otherwise, I'll type out the entire thing as a comment. And any other questions, do add them in right now while I type in the comment. Okay, yeah. So the question has been answered. So I guess that was heard. So anybody else, any other questions, do ask them. We have another 3 more minutes before we end this live session and close this entire course for good. Any other questions? Of course, even though we finish the course, even though we will delete the course in another 2 days, any questions, any inquiries, any type of help, if you guys require any assistance, you can always send us direct messages on Instagram, and we will try our best to help you out in any possible way. Anything at all, do let us know and we will try to get it done for you. So I guess there are no more questions. There is 2 more minutes left for the live stream. But thank you all for joining. Hope to see you guys in the next course, future courses that will be coming up from IEEE RAS PS University student chapter. If there are any other videos, we would really like to see all of you guys watching all of those as well. Thank you all for attending all of these sessions, 5 sessions, mathematical. I know it's not like a lot of the courses that you guys do attend online. These courses were very, very technical. They are pretty boring for most people who, when you think about robotics, you don't think about this side of robotics, and most of the people would be more interested in the coding section and things like that. But yeah, really, the way how robotics would not be going great without AI, ML, and all of that, it wouldn't work at all at the fundamental level without this kind of math. So this kind of math is necessary apart from the AI, ML, and all of that. So I guess with that, time's up. I didn't get any other questions. So thank you all for joining. Hope to see you again in any of the future endeavors. No more in the next course. No more in the next sessions of this course. Yeah. So thank you all. See you in the future endeavors of IEEE RAS PS University. Have a good day. Stay safe and enjoy life.